Welcome back, geometry students, and I am deeply sorry for how long that last video was. I really hope you liberally used the fast forward button, or when you were working through the problems on your own, you were faster and you were just using me to check your answers. Again, always get up, stretch, take a break if you need to, but let's try this part. This is much shorter than the last part, generally speaking. But yeah. It's a couple more things of quote-unquote basic probability that I want you to get to know. So, we're going to talk about the difference between theoretical and experimental probability. You might want to take a second to think, what does theoretical and experimental mean to me? Where have I heard those words before, etc., because that'll help narrow it down. So far, we've been calculating theoretical probabilities. That is, we've been basing them on possible outcomes of an event compared to the sample space, not what has actually occurred in real life. What actually happens in real life is called experimental probability, as is, it is based on the actual experiments of an event. So, what I recommend doing is grabbing 2 dice, because obviously you have 2 6-sided dice sitting next to you. If you don't, or something else, you can go to any site where you have a dice simulator. So here, I'm just going to go dice simulator. This is the one I use for Dungeons and Dragons sometime. And I want it to roll 2 virtual dice. I hit roll. I got a 5 and a 2. Roll again. I got a 1 and a 4. And even some of them, let's see, where is it? This one, roll dice online. This one you can even say, I want it to roll 2 dice. A 100 times. Oh, it won't let me go that high. 99 times. It's probably going to take a second to load. And what it's going to do is it's going to... I got a 3 and a 3 on that one. A 6 and a 3. A 4 and a 2. And I scroll down my list, and this is all of my dice rolls. And it gave me an overall average, too, which is fun. But... so out of 99 dice rolls, these are all of my lists. You can think of these as ordered pairs. First die, second die, 3, 3. First die 6, second die 3. First die 4, second die 2. Oop, I can highlight. First die 4, second die 2. And it's telling us the average, we don't need that. But, so you can either use your own physical dice or something like that, and I want you to roll 2 dice 36 times. And record what the numbers you got and the sum below. So for example, in that I got 3 and 3, which if I add those up is 6. So 3 plus 3 equals 6. That's how I'll write it. And then I want to go, the next one was 6 and 3, which is 9. The next one was 4 and 2, which is 6, etc. 46 times, or 36 times. And then, based on your experimental probabilities, I want you to calculate, or I want you to consider these probabilities. So all of these things, which these are the same ones we investigated above. So I want you to go ahead and do that. They're all going to be divided by 36. And you're just going to look at your list of 36 things and see how many times these things occurred. So pause, do that. Now, hopefully you did that. Hopefully you experimented. Because now we're going to go here. Are your experimental probabilities the same as the theoretical probabilities? The answer is going to be no. If you got them exactly the same, congratulations. There's actually a low probability that theoretical and experimental probabilities are exactly the same, which is confusing, but I'm going to say that anyways. But there's something called the law of large numbers, which is pretty straightforward. The law of large numbers says that as you do more experiments, the ratio that an event occurred will converge on the theoretical probability of the event. This means that if you roll your dice 3,600 times, you're more likely to get these numbers closer to what we got up here. Whereas if you roll a die 2 times, you're very likely it's actually impossible to get these exact things, because out of 2, you're only going to get 1/2 type things, or 2 halves. So, the law of large numbers says that to get experimental and theoretical probabilities to be the same, or close to the same, you have to do it more and more times. And if you have an easy die simulator, or you could create something in an Excel spreadsheet that does it for you and could even calculate the probabilities for you. You just have to code it correctly. You could get it to see if you do it 100 times what happens, if you do it 300 times what happens, and just see if those numbers converge to our theoretical probabilities. But we're not going to do that today. So that's one thing to know. Theoretical and experimental probabilities will be different. But the more times you do them, the closer they will be to the same. So that's something to keep in mind. So if someone tells you there's a 90% chance of the Seattle Seahawks winning the Super Bowl next year, that does not mean the Seattle Seahawks are going to win the Super Bowl next year. That means that they are more likely than not. But if I don't know, that was a weird example. If we tried the Super Bowl in 10 different parallel universes, they might lose the Super Bowl 5 of those times for all we know. I don't know. That example got away from me. Don't worry about it. But this also relates to what's called complement events, which I think of as not events. So the idea is the complement, not like a compliment as in, your hair looks nice today, but a math complement is an event of possible outcomes that are not the event. So for example, if my event is that today is Monday, if I, which during this quarantine it's felt like it, if I had to at random guess what day of the week it was, which it feels like that's what I'm doing a lot of the time, I would have a 1 in 7 chance that it's Monday. I'm like, it's Monday today. It's not, but I had a 1 in 7 chance of being right. The complement of that is it not being Monday. So if Monday is here, not Monday is all of this. Tuesday's not Monday. Wednesday's not Monday. Thursday's not Monday. Friday's not Monday. Saturday's also not Monday. And Sunday's not Monday. So all of these things are not Monday. Flipping 3 heads from a coin 3 times. So that'd look like heads, then heads, then heads. 3 heads in a row. So that's one option. But all of these things are not that option. So these are the complement. And the notation and formula for complement events can look like this. So, for example, if an event E, the complement is written as E with this little apostrophe. I think that's an apostrophe. And the idea of an event and a complement event is either the event happens or the event doesn't. So either the event happens or the complement happens. Therefore, the probability of the event is 1 minus the probability of not the event, or the probability of the complement of the event, and the probability of the event not happening is 1 minus the probability of the event happening. So, for example, I'm gonna look at this, I guess. You buy a raffle ticket out of 1,000 raffle tickets. The complement of winning the raffle, so winning the raffle is one thing, one event. Not winning the raffle is another event. So the probability you win the raffle is 1 out of 1,000. You bought one ticket out of 1,000 total tickets. While the probability of the complement, that means the probability of not winning the raffle, would be 1 minus 1 out of 1,000. Which is going to equal, we make this fraction. Let's prepare you a bit for Algebra 3-4 next year. We need to have like fractions to add or subtract. We need their denominators to be the same. So I'm going to multiply this by 1,000 over 1,000, because that's going to make it 1,000 over 1,000 minus 1 over 1,000. Because now I can subtract the 1,001 and get 999 over 1,000. So there's exactly one situation out of 1,000 where I won the raffle. Yay! But the complement is there are 999 different ways I don't win the raffle. So that's the idea of complements or not events. The chance that something doesn't happen. So that was the second part. Hopefully that was a little shorter, a little more bearable. I should have split it up a better, and I apologize for that. But thank you. If you have questions, please come into office hours. Please talk to me. I miss hearing you, seeing you, solving math with you. So come into office hours. You can work through the homework with me. You can talk about life. You can say, I don't know, whatever. So, yeah, that's it for this week. Bye.